right, if you were in the Zoom meeting, would have been yesterday, I said I was going to put a lesson in for chapter 13 today. Wicket, get out of there, please. Wicket, come. Gabby, come. Sorry. I said that I would post a video today for chapter 13, but it's not going to be due until after the test, so don't worry too much about getting this done right away if you want to focus on studying. So if you thought chapter 12 was fast, chapter 13 is even faster. There's really not a lot in this chapter. We're just going to finish it up because, hey, we can. And at that point, we'll actually be done any new work we're going to do. You'll have an assignment to do, but that will be it, and it'll be due by June 5th. So if we get this done early, that's great. That gives you more time to work on your assignment. Haven't decided whether I'm going to do like a big theory test or not. I likely won't, unless you think, hey, I'd really like one because I think it will boost my mark. I doubt we'll bother to do one. I'm so winging all this because I don't know what to do. But I think we'll just stick with the big math assignment and call it good. So chapter 13, like I said, is going to go very quickly. I wish I had my slinky here, but it's at work. My slinky would come in handy, but that's okay. We are going to, in chapter 13, talk about simple harmonic motion, and we've already talked about this before. So there's not a whole lot new in here. And the theory portion of it is mostly stuff you already know. So again, I'm going to post the PowerPoint for it. There is no PowerPoint for section 13.2. 13.2 is like pretty much nothing. So 13.1 is where the focus will be. So describing periodic motion. Any motion that repeats itself precisely over equal periods of time is periodic motion. Periodic motion is just motion that repeats itself. Now, even if it's a complicated motion, so even if it's this, that would still be periodic motion, okay? Because it happens, it's the same over equal time periods. Now, simple harmonic motion is generated by a linear restoring force, meaning think about a slinky. And I don't have a slinky, but let's at least use something. So if this were a slinky, okay, and I pulled down on it, it would do the same simple motion over and over again, okay? So we'll do it sideways. We're gonna end up doing it sideways anyway. When it stretches out, it has elastic potential energy, which forces the slinky to come back and convert into kinetic energy, and then it compresses so that it's got all elastic potential energy again, and then it keeps going in this repetitive motion back and forth. And that is a simple harmonic motion, and it all happens in a straight line, linear restoring force. When you graph that, however, what ends up happening is you end up with a simple waveform. And they explain how you could actually get that. If I had, say, a slinky, I had a spring, and I had like a writing tool on the end of it, okay, and I had this bouncing up and down and up and down, and I was able to have like a whiteboard move along behind it. As it goes up and down and up and down and up and down, it's going to create that wave, all right? It's not going to create this wonky wave. It's going to create this simple wave, simple harmonic motion. So simple harmonic motion is generated by a linear, straight line, restoring force. So both of these are periodic motion. This one, though, is simple harmonic motion. All right, so we're going to talk about the couple of terms that you already know. And we're going to talk about this, and you're going to need to imagine a slinky with a mass on the end of it, okay? So, but if we think of the slinky, as going up and down vertically, the problem with that is when we go to do the calculations talking about energy, not only is there elastic energy, but there's also gravitational energy, because both would be working in the same direction. If I turn it on its side and I start talking about it this way, suddenly gravity no longer plays a part, because that's going vertically and the periodic motion is going horizontally. And so now I've eliminated the need to work with gravity, and I can just work with elastic potential energy, which is easier because less formulas to deal with. So that's why we're going to deal with it on its side. Now, when physicists do the math and they try to figure stuff out, they deal with it in what we would call ideal circumstances. In other words, we ignore things like air friction and things that we know in real life would actually occur. So if we think about a slinky attached to a door or a wall or something, okay, and here's the slinky, okay, and it has a mass on the end of it. If we pull the mass and it starts going back and forth, we know that in order to stay horizontal, it has to be sitting on something, like a table or something, which means there would be friction involved. But we're going to pretend that there is no table there, and we're just going to deal with the idea of elastic potential energy. So when that slinky, I wish I had my slinky, but I don't. When that slinky is just sitting there, it's not stretched out at all, it's just sitting there in its rest position. That happens right in the middle, where the slinky's not stretched out and it's not all compressed in, all right? At that point, the slinky isn't moving, it's just sitting there. And so the only type of energy, well, it is, okay, so it's not moving. So there's my story, it's not moving yet, okay? Then a kid, say my nephew Caius, comes along, and being a kid and just being human in general, he decides, well, that looks like fun, and so he pulls on it and lets it go so that it starts moving back and forth, okay? When it is stretched out to its maximum, it is not moving at all. It is entirely elastic potential energy. And when he lets it go and it comes all the way in and compresses in, it stops for a second before going boing back out like that, right? So when it's in here, it's also all elastic potential energy. So as it's oscillating, that's the word, as it's oscillating, boinging, as it's oscillating back and forth, it reaches its maximum velocity when it is exactly in the center, okay? Elastic potential energy, and then it's all movement, all the elastic potential energy is converted. It is converted into kinetic energy. So here in the center, it's all converted into kinetic energy. And then when it starts compressing, when it starts coming in, it starts slowing down and it starts being converted back into elastic potential energy until here. It's all elastic potential energy. So if you're looking for what is the energy, say at this point, so sort of in between, it would be a combination. It would be some kinetic energy plus some elastic potential energy, right? Because it's all kinetic here, it's all elastic here. So in between, it's divided up. Some of it is kinetic and some of it is elastic. If you're closer to here, then more of it will be kinetic and less will be elastic. If you're closer to here, then more will be elastic and less will be kinetic. So the total energy then is equal to the kinetic energy plus the elastic potential energy. Now, oh, you're so cute. Energy cannot be created or destroyed, so the amount of energy stays constant through the oscillation. What changes is how it's divided up, how much of it is elastic and how much of it is kinetic. And we've done questions like that back in, I believe, chapter 7 or 8, somewhere in there. I think 7. All right. Now they do a whole bunch of talking about stuff on page 602 and 603, which is all about derivations of formulas, etc., 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 which we're not going to deal with. Now, the amount of times this thing oscillates per second, that is the period, right? The frequency is the inverse of period, and it's how many seconds does it take to do one oscillation. So period and frequency are inverses of one another, meaning they are the reverse, right? You flip the fraction over. But when we're talking about a mass on a spring, there is a formula for figuring out period, and period is 2 pi times the square root of m being the mass at the end of the spring, over k. And if you remember back at chapter 7, k is the spring constant, all right? Now, so that's a formula when we are talking about a mass on a spring. Got it? Mass on a spring, period, is that formula. I'm emphasizing that because in the next lesson, when we do the second half of chapter 13, we're going to talk about a pendulum, and we're going to talk about period for that, which is related to this, but not quite the same because it's not a spring. So it doesn't have a spring constant. All right. So when we talk about this, we're going to be talking about energy levels. We're going to be talking about period. So let's kind of make a list of formulas that we know. So that's the new one. But we also know that kinetic energy is 1/2 mv squared. I hope you know. And we know that elastic potential energy is 1/2 k times x squared. And x is the amount that the spring is stretched. Okay, so back in that diagram, I'll make a smaller one. Whoops. Back in that diagram, okay, went right in the very center, my x would be nothing because it's not stretched at all, right? Out here, my x would be whatever the maximum extension would be, and in here, my x would also be the maximum of whatever it can be because it's compressed in that amount. One technically should be positive and one should be negative, and we'll talk about that maybe a little bit as we go. So we're going to do one example on page 606, and here is the information we're going to use, and just one or two other things, but they're sort of logical, so that's why I'm not really writing it so much as a formula. So you stretch a spring a distance of 12 centimeters from its rest length, and then you release it. So here's its rest length, and you stretch it 12 centimeters. okay? And you release it. 125-gram mass on the end of the spring. Well, I'm going to change that into kilograms. 0.125 kilograms, that is the mass at the end of the spring. Completes 20 cycles, meaning it goes back and forth 20 times, in 15.5 seconds. So part A wants us to find the period, so T. Okay, so period, remember, is how long does it take to go through, it is how long, I just want to say it right. How long does it take to go through one full cycle? So it needs to be in seconds. So if in 15.5 seconds it does 20 cycles, it goes back and forth, I would divide those two to figure out how long would it be for one cycle. So if I do 15.5 divided by 20, I get 0.775 seconds. So the period is 0.775 seconds. It takes less than a second for it to go in and come back out, okay? To do one cycle. Part B says, what is the force constant on the spring? What is the force constant on the spring? So the easiest thing to do with the spring constant, the easiest thing we could do is, look, there's a formula with spring constant in it. I know the mass, 2 pi, well, I don't need, and period, I just figured out. So to figure out my spring constant, I'm just going to do period is 2 pi times the square root of m over k. So 0.775 is equal to 2 pi times the square root of m over k. So I would divide this side by 2 pi. So I would divide this side by 2 pi. So 0.775 divided by 2 pi, and I'm putting 2 pi in brackets just to be sure, gives me 0.1233, and it keeps on going, so I'm just not clearing it in my calculator, is equal to the square root of m over k. Now remember, I'm trying to find k, so I'm going to get rid of the square root by squaring this side. So I'm going to square this side. So I'm going to square my answer. So now I have 0.0152, and again it keeps on going, is equal to m over k. And I know my mass is 0.125 over k. So I'm going to multiply both sides by k. So I have 0.0152k equals 0.125. So I'm going to divide this side by 0.0152. So I'm going to divide this side by 0.0152. Now I'm just not clearing it on my calculator, so I'm going to do the whole number. I'm not rounding off. So I'm going to do 0.125 divided by my answer, and I get 8.21. So my spring constant is 8.21. So now I figured out my spring constant. So this was part A, this is part B, 8.21. All right? So part C. Part C says the total energy of the system. So the total energy. There's a couple of different ways that you could figure this out, but the energy is going to be the same at any point in the oscillation. The energy is never going to change. When it is stretched out to its maximum, so just before you let it go to do the bouncy thing back and forth, this is all elastic potential energy, all of it. So at this point, my total energy would equal whatever my elastic potential energy is, because all of my energy is elastic at that point. And elastic potential energy is 1/2 K times x squared. Okay, 1/2, I figured out K, that's 8.21, times x squared. Well, they said I'm going to stretch it out 12 centimeters. 12 centimeters would be 0.12 meters squared. So if I work that out, 0.12 squared times 8.21 times 0.5, I get that my total energy is 0.0591 newtons. Okay, so my total energy is 0.0591 newtons. Now they have 0.0592. That's because, and here's my point about rounding off, I used 8.21, the rounded off version. They used 8.21611. They used the whole thing. You really should use the whole thing. I have a very small board, not a lot of space, so I'm kind of condensing, all right? All right, so that was part C. The total energy is 0.0591. They actually say it's 0.05915 as their whole thing, which is why they rounded off to 592. Okay. All right, so part D wants to know the maximum speed of the spring. So we talked about this. Where does the maximum velocity, where does the maximum speed happen? It happens right here at the middle. Because when I have it completely stretched out, it's not moving. When I let go, it speeds up till it gets to its maximum speed. As soon as it starts compressing, it starts slowing down. So right here in the middle, where my x is 0, it is all kinetic energy. All of it. It's all kinetic energy. So all of that 0.05915 newtons of elastic energy is now kinetic energy. So my total energy is equal to my kinetic energy, which is 1/2 mv squared. So my kinetic energy is 0.05915 times 1/2 my mass is 0.125 times v squared. Now the only thing I don't know is v. So I'm going to rearrange this, and they say it is 9.73 times 10 to the negative 1. So really 0.973 meters per second is what they get, okay? And again, all I would do is I would do 0.05915 divided by 0.5 times 0.125, and then I would take the square root of that, and yes, I get the same answer. They do. That's good. All right, so now I have figured out D. See, no one piece is difficult, no one piece is long, but I kind of needed this piece to figure out this piece, and then I needed this to figure out this. Just take it one step at a time, okay? Now, the most complicated one, of course, is the last one, which is E. And they want to know what is the velocity when the mass is 10 centimeters from its equilibrium point. When it is 10 centimeters from its equilibrium point. So at that point, so let's say 10 centimeters is right here, right? If 10 centimeters is right here, okay, it's not completely, it's not at its maximum extension. So it is not all elastic potential energy. It's also not all kinetic energy. It is that mix, okay? So my total energy would equal my elastic potential energy plus the kinetic energy, because it's going to have some kinetic energy here at this point. It's going to have some kinetic energy and some elastic potential energy. So I already know that my total energy is 0.05915, because that amount is never going to change, because we're assuming an ideal situation where there is no friction. That is equal to my elastic potential energy, which is 1/2 K, and we figured out my K is 8.21, and really you should be using the whole thing, but I'm being lazy, times X squared. Now my X is 10 centimeters from its equilibrium point. So instead of, like in the first time when I did it, I used my X as 0.12, I'm now going to use it as 0.10 squared, okay? Plus 1/2 my mass again, 0.125, times my velocity squared. So you can see in all of this, the only thing I don't know is right here. So I'm going to take this part, whatever this is, and move it over here and subtract it. So I'm going to have 0.05915 minus whatever 1/2 times 8.21 times 0.10 squared is, and that's going to equal 1/2 times 0.125 times v squared. So I'm going to do 0.5 times 8.21 times 0.1 squared, and I'm going to do 0.05915 minus my answer. So over here, I'm getting 0.0181, hopefully that's right, and here 0.5 times 0.125 is 0.0625 v squared. So I'm going to divide both sides by 0.0625 and take the square root. So 0.0181 divided by 0.0625, take the square root of that, and I get 0.538, because there are 3 significant figures, 0.538 meters per second. So that is how fast it's going when it's 10 centimeters away. Now, let's do some logical thinking just for a second. I know it hurts. But we figured out that the maximum velocity it should be when it's here in the middle is 0.973. So the velocity should be less when it's out here, because it's almost completely stretched out, which means it's almost completely stopped, right? Another 2 centimeters and it's reached its maximum extension, and it's going to start moving back in again. So it should have slowed significantly. And it has. It's gone from 0.9 down to 0.5. It has slowed significantly. So that makes sense. Okay? So that's it. That's all we're doing. And again, I don't really think there's a whole lot new except maybe this formula. But this stuff you already knew. So I'm going to give you a few to try. It will not be due until, hold on, we're doing the test on Thursday, so it won't be due until Friday is when it will be due. So you have until Friday to finish this, so that you also have time to study. Again, this chapter is going to fly by. Just word of warning, word of promise, I don't know which it is. I did some lesson planning, and I have like a few blank days where I just kind of put, I don't know if I'll need to catch up or not. So I put test next Friday, which would be May 22nd. And I don't see any reason why it shouldn't be, but that's how quickly we're going to go through this, okay? So we haven't even done chapter 12, and I'm already talking about a test for chapter 13. It'll be short. And then after that, there are 2 weeks left of school, and I don't have anything new to teach you. It will simply be, I say simply, simple for me, But it's going to be working on that year-end assignment that is going to take the place of an exam. So again, let me caution you. I don't have to caution you guys quite so much as the younger people in the group, but don't rush through it to say, hey, I'm done and I don't have to work on it anymore. You want to do well on it. So even if you limit it just to 2 or 3 questions per day, but doing a good job on those 2 or 3 questions per day, you would have it done by June 5th. What I would hate for somebody to do is to rush through it, not check it over, not really pay attention, and not do well on it. You can ask each other for help on it. I'm not going to limit that because I don't really know how I could. So I'm not going to limit any of those things. If you need help, you can certainly ask me to do a question like. A lot of stuff is already on YouTube. You can go back to a particular lesson and watch that video again. But if it happens that there isn't a video for that because we did it, when we were actually still in school, I can make a video for that as well if you need me to. If you want to do a Zoom meeting so we can talk through something, that's certainly an option as well. Whatever you need, however you need me to help you, that's what I'm here to do. But I also don't want to make the end of the year where everybody's piling a million things on you and you have no time to do anything. So I'm trying to plan this out so that you have time to be working on things where you're not getting anything new from me, okay? So that's my plan going forward. So we'll talk to you again. Good luck on your test if you're watching this before you write your test.